Hey everyone, in this video we're going to be taking a look at a few strategies to make quick sketches of rational functions. So whenever we have a polynomial divided by another polynomial, we say that's a rational function. So in this video we're going to take a look at 3 examples here over on the left side, and you could click on these examples at any time to go straight to that example. And once we finish those 3 examples, we're going to take a look at the summary of steps that we used in making sketches of these 3 rational functions. Now, for number 1 here, we have f of x is equal to 1 over x plus 3. Now, to make sketches of these rational functions, typically it's not as easy as just picking an x value and finding a y value and plotting all these points. It's going to take a very, very long time to get an accurate picture of what the rational function would look like if you just plotted points. So we need to have some type of strategy to use when coming into these types of problems. So we want to try to determine a few things first here. When we start with these rational functions, it may be advantageous to factor either the numerator or the denominator or both if you can. But in this particular case, we cannot do that. So the next thing you may want to do is determine the domain of the rational function that you're working with. And to determine the domain, generally what we're looking at is we're trying to find the restrictions on our independent variable, whatever that happens to be. In this case, our independent variable is x. So if we find any restrictions on x, we're going to go ahead and take it out of the domain. Now, in this case, when looking at the denominator, we see that we have x plus 3 down there, and we know that we can't divide something by 0. So whatever x value makes this denominator 0 is going to be a restriction on our domain. And so we may go over here. We could say, actually, let me go right here. We could say x plus 3 cannot be equal to 0. Because we can't divide by 0, so x plus 3 can't be 0. And if we just do the math here, subtract 3 from both sides, we get x cannot be equal to negative 3. So this is a restriction on our domain. Now, 2 things could happen at our restrictions here. Either you're going to end up with a vertical asymptote, which is where the graph will approach it in the x values, but then it's going to shoot up to either infinity or negative infinity. Okay, so that's the vertical asymptote. Or we could end up with a hole in the graph where the graph appears to be smooth and it appears to go through that point, but really it's a restriction, so there's going to be a little pinhole in that area. And if you go to graph these on a graphing calculator, these holes are really hard to show on a graphing calculator, so if you were to do it on a graphing calculator, you may not be getting a complete picture of what's going on. So we see we have restriction at x is negative 3. So what we're going to end up here is we're going to end up with a vertical asymptote. Now, the reason I know this is because once the rational function is completely simplified, okay, it's whatever the restrictions happen to be, we're going to have a vertical asymptote at that spot. Okay, the holes appear when you're able to simplify this function further, and it looks like you get rid of some restrictions, but really they're still there. So that's going to be example number 2, but in this case, we're going to have a vertical asymptote here. So to draw a vertical asymptote, we go to this area, x is equal to 3. Then we're going to go ahead and draw in a dotted line. And this will represent our vertical asymptote. So this is something the graph cannot cross. And you can have multiple vertical asymptotes in your rational function as well. In this particular case, we only have 1. Now you may recognize this function as being the translation of our basic 1 over x reciprocal function. This is going to be that function translated to the, I did that at 3, didn't I? I meant to do that at negative 3. Let me get rid of that dotted line here. Okay, so we go to the left 1, 2, 3. X is -3 here. And we're going to go ahead and draw our asymptote. There we are. Okay, now that's correct. Now this is the basic reciprocal function translated to the left 3 units, right? When you add something to the input, we're adding 3 here. That's going to translate it left. So it should look like that function just moved over to the left 3 units. So we could go ahead and graph it like that, but let's take a look at a few strategies here. Next thing you may want to do is locate any values along the x-intercept. So for the x-intercept, we know that the y value is equal to 0. Okay, and now in this particular function, in order for a fraction to be 0, it needs to be 0 over some number that's not 0. So 0 over any number except 0 will give us 0. And this numerator is 1, so the numerator here is never going to be 0. So in this particular case, we're not going to have any x-intercepts. What this ends up being is a horizontal asymptote. So this x equals -3, this is called a vertical asymptote. Let me write that in. Now, if you remember the rules for horizontal asymptotes, if the degree of the numerator is less than the degree in the denominator, we're going to have a horizontal asymptote at 0. So when y is equal to 0, we have a horizontal asymptote. Okay, so we could go ahead and draw in a dotted line here, but it's covered up by the solid line, so we'll just use our imagination. So what that means is that the end behavior of this function is going to tend towards 0. When x gets really, really, really large, the graph is going to get close to 0. Like if x were 10,000, 1 divided by 10,003, it's a really small number. Or if x were a negative number, like -10,000, then this graph is also going to approach 0, but on the negative side, or to the left of the y-axis. And now, unlike the vertical asymptotes, it is possible for the graphs to cross a horizontal asymptote. It could cross it numerous times. In this particular case, we're not crossing the horizontal asymptote, though. Now, next up, once we have these asymptotes figured out, you may want to look at a couple points immediately to the right and immediately to the left of our vertical asymptote to help us determine the behavior. So if we take a look at the point -2, so if x is -2, then we're going to have 1 over 1, which is 1. So we have a point -2, comma 1. So we're sitting right here. So right there, that's going to completely determine the behavior on the right side of our vertical asymptote. We know that as the graph moves to the left, we are not going to cross this vertical asymptote, and we're also not going to cross our x-axis, right? So, because we don't have any points where the graph, where y is equal to 0, they don't exist. So we're never going to cross our x-intercept. We're never going to cross our vertical asymptote here. So as we get closer and closer, we're going to shoot up towards positive infinity. And as we move away from it, the end behavior is going to get closer and closer to y is 0. So as we move further to the right, we're going to get closer and closer to the x-axis, but we're never going to touch it. So now we're going to look immediately to the left of our vertical asymptote. So maybe at a point -4. So if x were to be -4, this would be 1 divided by negative 1, which is negative 1. So we have a point negative 4, so 1, 2, 3, 4, negative 1. Here we are. So we know as we get closer to the vertical asymptote, we are not going to cross the x-axis again, so it's going to have to go in one particular direction. It's going to have to go down. And as we get closer and closer to it, we're going to shoot towards negative infinity there. And as we move to the left here, our end behavior is going to tend towards a height of 0. But we're never going to actually hit that line just because there's no possible way for this function to be equal to 0. So we're going to get closer and closer to our horizontal asymptote, but we're never going to actually touch it. So here's our sketch of the graph. Again, it looks like our basic reciprocal function, 1 over x, but it's translated to the left 3 units. So now let's go ahead and use some of those strategies and see how number 2 is going to be different from number 1. So in number 2, we have f of x is equal to x minus 3 divided by x squared minus 9. So as I had mentioned in the previous example, we may want to factor anything if it's possible. So we can't factor x minus 3, but we can factor x squared minus 9. This is the difference of two squares, and this is going to be x minus 3 times x plus 3. So now, at this point, it is possible to reduce this, but let's leave it like this here. Let's go ahead and take a look at the restrictions on our domain at this point. So we said that the denominator cannot be equal to 0. So what values of x are going to make the denominator 0? Well, if x were 3, this would be 0 times 6, which is 0. So x cannot be 3. And if x were negative 3, this would be negative 3 plus 3, which is 0. And this would be 0 times negative 6, which would be 0. So x can't be positive 3, and x cannot be negative 3. So we have to determine whether these are going to be holes in our graph or vertical asymptotes. And here's how we can tell. We're not sure at this point, but what we want to do now is go ahead and simplify this expression. If we simplify this expression, let me rewrite it down here. We have x minus 3 divided by x minus 3 times x plus 3. We see that the x minus 3's cancel out, and we're left with 1 divided by x plus 3. Now that was exactly our previous example, right? But this 1 over x plus 3 is not the same as this 1 over x plus 3. The difference is in our domain. Okay, in this particular case, our domain excludes the value of positive 3 as well. All right, so the restrictions that remain, right, here we see that x cannot be negative 3. If you have a remaining restriction after you simplify it, that's going to turn into a vertical asymptote. So at x cannot be negative 3, we will get a vertical asymptote, and I'll just abbreviate that VA. And the restrictions that seem to disappear, right? If x were 3, we would get 1 over 6, right? That's perfectly fine at this point. But we know that 3 is not in our domain. So what's going to happen is this point, at x equals 3, we're going to get a hole at that particular point. Right? So the picture is going to look exactly the same, except we're going to get a hole at x is equal to 3. So let's go ahead and graph this again. So we have our vertical asymptote at x is equal to negative 3. So we go ahead and draw our vertical line there to represent the vertical asymptote. And I said we get a point at negative 2, 1, and at negative 4, negative 1. So as we get closer to this asymptote, we're going to go down. Oop. Okay, there we go. And again, our horizontal asymptote is the same. Looking at the simplified version, Is there any way for this fraction to equal 0? No. And again, if you look at our function here, the degree of the numerator is 1, and the degree of the denominator is 2. When the degree of the numerator is less than the degree of the denominator, we're going to get a horizontal asymptote at 0. And again, it is possible to cross the horizontal asymptote, but in this particular case, we are not crossing it anywhere. So as this function moves further out, the end behavior dictates that it's going to get closer and closer to 0. And we're going to get the same thing here on the other side. And we're going to move right here. Okay. So now, when you're at the end of your function here, identify where the hole is. Now, when x is 3, we're going to use our simplified form here to see what we get. Like if you try to plug 3 into our beginning function, we get 0 over 0, which doesn't help us determine where the hole is. So if you want to know where the hole of the function is, we're going to look at our simplified form, and we're going to evaluate it at x is equal to 3, and we get 1 over 6. Alright, so here's x is equal to 3, that's about 1/6. So our hole is going to appear right here. So generally we do an open circle to represent a hole in the graph. So the graph goes towards that open circle, it stops, it skips that particular spot, and then it continues on. Now again, in a graphing calculator, you're not going to see something like that. It's going to look like the graph goes right through that open circle. So now, let's go ahead and take a look at example number 3. We have f of x is equal to x minus 2 over x squared minus 3x minus 4. So when looking at these rational functions, again, we want to try to start with factoring if at all possible. Now we can't factor the numerator, that's going to stay as x minus 2. But the bottom is going to factor as x minus 4. So we have x minus 4 times x plus 1. So by factoring it, we're going to see the restrictions on our domain much easier. So now we're trying to determine the domain, and we see that x cannot be positive 4, and x cannot be negative 1. Now, is there any way to simplify this fraction here, x minus 2 over x minus 4 times x plus 1? No, it's as simple as it could get. Nothing cancels out. So because these restrictions remain in the simplified form, both of these restrictions are going to turn into vertical asymptotes. So we don't have any holes in the function, but we have a vertical asymptote at x is equal to 4 and at x is equal to negative 1. So let me go ahead and draw those in. Here's 4. And let's do our vertical lines to represent the vertical asymptotes. Okay, and at x is negative 1, we do our dotted lines here. Okay, great. Now, to get a more accurate sketch of the picture, we may want to determine, do we have any x-intercepts? So is the graph crossing the x-intercepts, or the x-axis anywhere? And the x-intercepts occurs when y is equal to 0, or the function as a whole is equal to 0. And the only way for that to happen is for the numerator to equal 0, while simultaneously the denominator couldn't be 0. If you got 0 over 0, that's an undefined quantity. So it looks like if x minus 2 is 0, then x would have to be 2, right? So if x is 2, what do we get for the denominator here? So we get 2 minus 2 divided by 2 minus 4 times 2 plus 1. Okay, so this is 0 divided by, we get negative 2 times 3, which is negative 6. So that's perfectly fine, right? 0 over negative 6 is 0, so that value of 2 works. Again, we were just looking to see that we don't get 0 over 0. So we do have an x-intercept, which is going to be the point 2, comma 0. So here we are at 2, comma 0. Now, we may want to look at a few points immediately to the right and to the left of our x-intercepts here. I mean, our vertical asymptotes. So immediately to the right, maybe we'll choose a point if x is 0. If x is 0, we get 0 minus 2 divided by negative 4 times 1, which is equal to 1 over 2, right? Negative 2 over negative 4 simplifies to 1 over 2. So we have a point 0, 1/2. Okay. So now this is going to completely determine our behavior. In between these vertical asymptotes here, it's only possible for a graph to look like this, where as it approaches the left one it goes up, and as it approaches the right it goes down. Or we could have the opposite case here. As it approaches the left asymptote it goes down, and the right it goes up. Or we could have something that looks like a parabola, where as it approaches the left asymptote it goes up, and as it approaches the right asymptote it goes up. Or as it approaches the left it goes down, and the same for the right, it could go down as well. So these are the 4 cases. Now we know that the function only crosses the x-intercept at one particular point, so therefore it can't go down at this point. So it's going to have to go up as we move to the left, and of course it will never hit that asymptote. It'll never hit that asymptote there. And as it moves to the right, we're going to cross through this point, and then it's going to move. Let's do this. And as it moves to the right, it's going to move down here. Okay. And you could check a couple of points over here as well. Like at a point x is equal to positive 3, let's say. Let me get rid of that part of the graph. What I should do is I should first check to the left of this vertical asymptote. If x were to be 3, for instance, are we going to be above it or below it? Well, this will turn into 3 minus 2 all over 3 minus 4 times 3 plus 1, and this is equal to 1 over, now that's negative 1 times 4. Okay, so this is negative 1 over 4. Okay, so at 3 we're at negative 1 over 4, which is about here. Okay, so again, since we only crossed the x-axis one time, we're not going to go back up. We're going to continue down right here. All right, so that's the middle of our graph here. Now we want to check to the right and the left here. So now, to the right of this asymptote here, we could choose a value of 5. So we would get 5 minus 2 on top, which is 3, divided by 5 minus 4, which is 1, and 5 plus 1, which is 6. So this is 1/2. So the value of 5, we're at 1/2, which is right here. So since we cannot cross this x-axis again, we would suspect that as we move to the left, we're going to move up here. And as we move to the right, our horizontal asymptote is at 0. Is at y is equal to 0. So we're going to tend towards that with our end behavior. So as we move to the right, as x gets larger and larger, we're going to get closer to 0. Now we just need to check one more point to the left of this asymptote here. Let's say -2. If x is -2, then we're going to have -4 in our numerator divided by -6 times -1, which is -4 over 6, which equals -2/3. Okay, so we have a point at -2 and -2/3, which is about here. So we know the graph can't go up here because it would be crossing the x-axis, and we know that we only cross it at one point. So it's going to continue down at this, continue down here at this point. It's going to get closer and closer. Okay, and then as it moves to the left, our horizontal asymptote is at y is equal to 0. So we know it's going to get closer and closer to that point as we move to the left. And there's our quick sketch of number 3. And you could check that in the calculator here to just see if you're accurate enough for your sketch. Now, since we're done with the 3 examples, let's take a look at the summary of steps that we use to sketch these rational functions. So for the rational functions, and this is just a polynomial divided by a polynomial, we have a series of a few steps here. It seems like a lot, but it's not too much. So the first thing we did was we factored the numerator and denominator of the function. And we did this because it was going to help us determine the domain of the function, and it's going to help us find the restrictions on the independent variable that make the denominator 0. The next thing we did was determine the values of the independent variable that make the numerator 0 and are not restrictions. And then we wanted to plot those points. Those are the x-intercepts. Next, we reduced the function by canceling common factors. If you had restrictions that remained after the simplification, those are going to turn into vertical asymptotes, and we drew those as dotted lines, vertical dotted lines. The restrictions that were canceled turned into holes in the graph. So we saw that in example number 2. Now, next we wanted to plot points on both sides of the asymptotes to determine the behavior of the graph. And now we could use the calculator table to determine the end behavior if we wanted, but you could also use what you know about horizontal asymptotes, where when x gets really large, the y value may tend towards a certain value, which is the horizontal asymptote. So we could use that as well. But if there's any little hills or bumps along the way, it's very hard to tell, and we would need calculus to determine that. For 7, we wanted to draw the graph and place open circles on any of the holes. So the very last step in number 2, after we drew the graph, if we knew there was a hole, like at x is equal to 3, we just did a little open circle there. And then you may want to check the validity of the graph with a calculator. So again, calculators, they may not do too well with the asymptotes and the holes, but if you know what you're looking for, you could get a fairly accurate picture or a good idea of what's going on in the calculator. So I hope you enjoyed this video, and I'll see you in the next one.